Here I go. So I doing this problem with the student in the office. Oh, this is a good one. This is sweet termination. Might as well share with everybody. So if you have two radicals, say you have this blue radical lone electron and the red one on this guy, they can react in a way to make an alkane and an alkene. And using colors, hopefully you can see it better. So there's one hydrogen on the carbon with the blue radical. That one radical reaches over and gets one of the green electrons from this bond. There's two electrons in that one. So this hydrogen with the green bond, it becomes bonded to the other cyclopentane. So they got like a blue-green bond here, two electrons. And then the alkene's caused by the green electron in there, and the red there. So there we go. It's a fun one. I like these kind of mechanism. They're almost like little puzzles. I think I've seen little booklets. They're like, oh, mechanism puzzles, try to draw a curved arrow mechanism. That makes sense for this. It's something fun to do on the side, have little challenges like this so you can figure out. Okay, because the better you get at mechanisms, the easier this class is. All right, so today we'll probably finish chapter 3, I think, and then start chapter 4, cycloalkanes. Go from alkanes to cycloalkanes. You can come and do lab work before my first lab period of each day, Monday through Thursday. And I updated the times a little bit. I said one, I used to be you can come in at 1:30 on Monday, Wednesday. I think 1's okay. I was just trying to give myself enough time to, my goal was after the lecture to be able to download the video from the lecture, put in iMovie edit, upload to YouTube, link it to our site. So it's done quickly within that day. So if you come on Monday, Wednesday, I'll probably be in my office. I won't be have a lot of time to help you do things, but once I get the video up, I can help you more if you need it. And then Tuesdays, Thursdays are good days, 9 to 10:40, 10:35. Oh, and I made the end time different. So like my Monday, Wednesday lab starts at 2 p.m. So I want you to be all cleaned up before 2 p.m. so that those people can come in and if they have a quiz or something, they don't have to have goggles on because you have chemicals out. Same with the Tuesday, Thursday, the first lab is 10:45. Okay, I have a new extra credit assignment. Do another IR NMR unknown. So most of you have gotten all of your unknowns done. You gotten your ethyl acetate and toluene run and your unknown done. So, but I still like you to use the NMR because the more we use it, the better you get at it. And so over the next, I don't know, couple months or something, you should all try to do extra unknowns, to do the IR and the NMR, and then fully label them, turn them in 2 points extra credit, and you can do it up to 3 times. So that's actually a lot of extra credit. Afterwards, I was like, oh, I should have made it plus 1 point. But then Brenda was on top of it. She already did 2. So I was like, forget it. It's okay. It's all good. I'll just make the next exam super hard to make up for all the extra credit. Just kidding. It's all right. No, extra credit's good. All right. And then determination of unknown structures. That lab is due not for a while, but I mean, turn it in right away. I've already got 1 turned in. Keep turning them in because I think most everybody has all of their unknowns and their partner's unknowns, and they have ethyl acetate time. So just label them all up and turn them in, and answer those questions in the the lead up questions, but I think most of you are pretty much almost done with. So get that off your to-do list. Solubility of organic compounds. I did change the due date. I pushed it back to the 8th, but try to turn it in this week if you have it done. Then homework B, that's due today and tomorrow, the chapter 2 homework. So turn that in either today or tomorrow, or online or in person with a paper copy. And then NMR and IR labeling, a lot of times students make mistakes with that, like during this assignment. So a couple of things will help you. I'll have a quiz on it, and it's going to be next Monday, Tuesday in lab. But also, before you turn these in, if you want, you could show me, hey, can you glance at this really quick, see if I did it right? So I can point out, like, oh, fix that before you turn it in. Yeah, so a lot of times students make silly mistakes on that. Quiz coming up, and then I made up the homework C. I updated that, and I added a lot to it. I've kind of changed my philosophy on homework. Before it was just like homework was just some problems that are like exam, like here, get you ready for the exam. But not so much basic problems, but more exam, kind of a little bit more challenging problems. But now I've decided, oh, you know what, I'm going to add the basics into the homework as well. So if when you're studying chapter 3 material, I've got a lot of good stuff in there for you. So if you just start at the beginning of this homework, it'll have you first just like work on the mechanism for radical halogenations and then go into the reaction order diagram and the rest. So check that out. And then it also has chapter 4 problems, but I put the chapter 4 problems later in the assignment. So, and even, I'll show you real quick. I even like labeled each problem. So like this first problem, number 1, it's from chapter 3. So you should be able to do it. And it's just to click through the animation and write out the examples. And then question number 2 is chapter 3. So you can just go down the line and like, most of these are chapter 3, and then towards the end, I've got I threw in a couple of reviews. I think it's good to throw in some reviews, some Newman's. And then, so from homework number 13, you see, oh, that's from chapter 4. We haven't covered that yet. So if you get to that far along in this homework and we haven't covered that material yet, you can, just hold off. And okay, so exam 2 is in a couple weeks. So as I was saying last time, study this material as if it's the exams this Friday. So whatever we're doing right now, learn it. It's more efficient to learn it now than later. And the schedule, I'll let you check it out. It's pretty much got what I listed here. And then I updated the last question of the solubility of organic compounds. So you probably downloaded that Google Doc a while ago, and you won't see the update unless you go to the newest version online. So if you're having trouble with that last question, I think it's question 54 or something like that, you'll see I made it much more clear. And clean it up, don't pass it up. I remember when I was in a grocery store, they would have their thing was, don't pass it up, pick it up. Like they're like, if there's a spill or something, don't think someone else is gonna clean it up, do it yourself. Or the other ones they had was like, how many days without a workers' comp claim? Like, be safe, clean up a spill so nobody slips and things like that. So we can do a little better in lab. Sometimes I'll look over by the scale and I'll see solid. So somebody was weighing out something and they didn't do it in the scale, which is great. It's not on the scale, that's good. But they got it on the counter and then they just left it. And then maybe this was the first person and then the next person was like, oh, without even thinking about it in the back of their brain, they're like, oh, I guess if I spill something here, it's okay. Because see, that's the standard now. So don't do that. Take this is a paintbrush here, brush it on a piece of scratch paper, put it in the waste container. And when you put stuff in the waste container, I refer to it as the orange waste container, but then Mary pointed out it's more of a red color. We'll say it's a dark orange. Maybe that'll make construe red. But when you put things in there, a lot of times you'll drop it on accident because it's like, it's slippery. But don't just say, oh, well, there's a test tube in there, I'll just leave it. Let me know so we can get it out. Because when the stockroom was emptying it the other day, and I don't think this is from your class. I think this is from like pre-pandemic class. It's been a while since it's been empty. But there was like, she said there was like 6 test tubes and some NMR tubes and some bunch of pipettes and other stuff. So if you drop something in the waste container, let us know so we could get it out. So I don't look bad. It look like I'm not teaching you guys good stuff, good technique. All right, and then the Black Student Union is helping people out, and you can help them out as well. So our former SOTW, Cozy, is helping you help the less fortunate. So make a donation and let me know. I made an assignment in Canvas, and you can get an extra credit point, and then you get plus 10 karma extra. I should say good karma points. Some not bad karma points, good karma points. So yeah, donate some of these. You can drop them off in the Winstead building, or if you want, if Cozy maybe it gets like a cardboard box, you could put it in my office. Either way is fine. And then join a Sierra College club and get extra credit as well. So Cozy, I added an extra credit point for you already. I think you're here. Is Cozy here? Yeah, Cozy's here. So congratulations, Cozy. You've already got that extra credit. So if you're in any clubs, let me know on this assignment in Canvas, and then you'll get points for it. And then also I keep track of that. So in the future, if you ask for a letter of rec, then I can say, oh, Cozy was an important member of the Sierra College community. She was a member of the Black Student Union Club, and then maybe you're part of ECOS or something like that, whatever it is. I put that in there. It looks good on the letter of rec. And we have a new SOTW, a Western Sierra Collegiate Academy graduate. Human development major from Davis, now taking prereqs for podiatry or physician's assistant school. So already got her degree at UC Davis, but taking the prereqs, and has an interview coming up with Yale for their physician's assistant school. So that's kind of cool, might go to Yale. And so she's deciding between physician's assistant school or podiatry school. Podiatrists are doctors who concentrate on the foot. And then played volleyball for a club and school. First generation American, parents are from are Russian and Ukrainian, from Russia and Ukraine. Okay, I don't know, I said Russian, from Russian. And then plays acoustic guitar. Broke skull once, had a brain hemorrhage, fell from her attic at age 8, they induced a coma, and she recovered fine. So that stuff's crazy when you have to get an induced coma. Has had a cat since 3rd grade named Buddy. And here's Buddy. Doesn't look too old, huh, Buddy? Looks cute. Big fur ball. And our SOTW is Livia. I'm going to say the last name wrong. Not Donets, but Donets. I think it's Donets. Livia Donets. Let's give her a big round of applause. Our new SOTW joining the royalty. Coatsy started it off. Oh no, I'm going to forget who else. Brandon maybe was next. Alex, and now Livia. I think that's everybody, right? So far. Yep. Good job. Okay, so any questions from the intro stuff? Okay. So if no questions, then I'll start back in chapter 3. That's the homework. So in chapter 3, we're doing the radical halogenation of alkanes. Chapter 3 is basically like one reaction, and Hammond postulate. So let's review our radical halogenation of alkanes real quickly with our bromination PowerPoint. I'm going to bring it up on my end. Documents. Wait, was that right there?
What's that, bro? What's up, bro? Yeah, professor. More.
Like radical halogenations?
Okay, so we got the overall brodaceous reaction. We have for here, we have 2-methylpropane. We're going to brominate it. So we'll get the primary bromide and the tertiary bromide and HBr. Does anybody have a guess at what the major product would be? Which would be made the most, the tertiary bromide or the primary bromide? You know what? I think I'm going to pause on this for a second. Let me pause on that. Let me go over here and do this. I was just thinking about this. Let me make sure we're good with primary, secondary, tertiary stuff before I just keeps talking about it. I kind of last lecture I just started saying primary, secondary, tertiary with without much intro into it. I want to make sure you're following along with these terms. Okay, so I'm gonna draw a big molecule here. Okay, so If you are a carbon with only one other carbon attached to you, what are you? Are you primary, secondary, tertiary? You are primary if you only have one other carbon attached to you. One other carbon directly attached. Okay, and then what about this one right here? This guy, what is that? It's a carbon, and how many other carbons are attached to it? 2, so you're secondary. Only 2 other carbons directly attached to you. All right, that's secondary. What about this one here? Tertiary, right? Only 3 other carbons directly attached to you, tertiary. And then this one right here, what is that one? Quaternary, yep. I shouldn't say only, I should just say 4. All right, so 4 other carbon attached to you. So with that in mind, what's this guy? Primary, secondary, tertiary, quaternary. That one is secondary. This one over here. Tertiary, good. And then this one right here. Primary, got it, got it. What about if I just have like the molecule methane, CH4? Do you know what you call that? Would you call that primary, secondary, tertiary? So this one actually, it's not primary or secondary or tertiary or quaternary. It's none of those. What it's called is just methyl. It's the molecule is methane, but it's called, like if you refer, usually it's what I'm getting at is you refer to what's attached to it. So let me show you what I mean. So if I have now a molecule like this, let's say, this hydrogen right here, what do you think we call this hydrogen? Do you think we call that hydrogen primary, secondary, tertiary, quaternary, or methyl? That hydrogen is a tertiary hydrogen because it's on a tertiary carbon. That makes sense? Cool. What about this one right here? What's this hydrogen? Yeah, that's a primary hydrogen. And then if I draw another one, this guy right here, what's that one? Secondary hydrogen. You got it. Looking good. Let's do one more. Let's do this guy. Let's go boop, 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 boop. Okay. If I put a bromine right here, what kind of bromide do you think this is? Primary, secondary, tertiary? Tertiary bromide because it's on a tertiary carbon. And then if I have like this guy, what kind of bromide is that? Secondary bromide. All right, we're getting it good. And then what about this guy? CH3Br. Anybody know what we call that bromide? Exactly. Methyl bromide. It's not a methyl. It's not a primary, secondary, tertiary, anything like that. All right, cool. Let's go back to my animation here. I'll do the beginning again quick.
What's that, bro? Here, check this out, Professor. More.
All right, so here's the overall reaction. Primary bromide, secondary bromide. It makes sense that it's primary, right? It's on a primary carbon. Makes sense that it's tertiary on a tertiary carbon. So does anyone have a guess at what the major product is for these two? Is it the do we make more of the tertiary bromide or the primary bromide? Yeah, we make more of the tertiary because it's faster to form that radical. It's 1700 times faster to form this radical, tertiary radical, than the primary radical, and that tertiary radical leads to the tertiary bromide. Okay, so let's look at the mechanism real quick. Initiate radicalness. Boom, boom. The 2 electrons in that single bond break apart, make our radicals. No radicals, 2 bromine radicals.
Nice potato chip.
You're welcome.
That's not all protein shake.
And then now propagation step 1, a propagation step is one that starts with a radical and ends with a radical. And we're doing it for the primary bromide product. So here we go. We got a bromine radical to start. And how does it meet?
I can't go any further than this. Can you see me halfway?
Halfway, right?
The borderline is where I'm going away for you.
So we propagated the radical chain. We started with a bromine radical and then with a carbon radical. And it's a primary carbon radical because it's on a carbon that's only has one of the carbons, it's a primary carbon. And then
I get my props. I'm radical start to finish.
I was just noticing, I liked how before when this first one it started off with Fergie going, ooh. And I think this guy gives us a good ooh later to the skinny bodybuilder. Propagation step 2. So now I'm going to finish off this primary bromide product by starting with that carbon radical that was produced in step 1, and not a bromine radical to react with it, but Br2. So when this reaction occurs, only a very small amount of bromine radicals made. So once this carbon radical is made, it's way more likely to run into Br2 to make our product.
Can you see me halfway? Right, the borderline is where I'm going away for you.
All right, there we go. So we started in this one. The last one, prop 1, we started with a bromine radical to carbon radical. Here we have carbon radical to bromine radical. And now you can see this bromine radical can go up and react with another alkane.
Ooh, that's a lot more.
Ooh.
Oh yeah, I'm all about more Teddy Roosevelt.
All right, and then now we made the primary bromide. Now we're gonna work with the tertiary bromide. So I got an alkane, not radical, and then a bromine radical.
Can you meet me halfway? Can you meet me halfway? Can you meet me halfway?
One bromine radical, one carbon radical.
Can you meet me halfway? Meet me halfway.
And then meet me halfway again. It's a bromine radical, carbon radical to bromine radical. There we go. And then, so the tertiary carbon radical is made, then it comes down and reacts with the Br2. And that makes another bromine radical, comes up, reacts with an alkane to make a tertiary radical, which reacts with the Br2 to make a bromine radical, which reacts with bromine alkane to make carbon radical. So you can see the chain mechanism.
Next OChem exam, expect radical halogenations and a whole lot more.
All right, so now some terminations, which aren't really as important. I don't put them on the reaction coordinate diagram. They don't happen that much. They only happen at the very end of the reaction when your bromine and your alkane are like almost gone. So then there's this low concentration of radicals can start to run into each other and terminate the radicals. So here's one, any 2 radicals. So we got
Can you see me halfway?
2 bromides.
The borderline is where I'm going away for you. Can you see me halfway? Right, the borderline is where I'm going away for you.
If I were you on the exam, if you're doing a termination like this, I would definitely number and letter because it's so easy to leave off a carbon otherwise. Here's a cool one, the one I had at the beginning.
Meet me halfway. Right, the borderline is where I'm going
make an alkene. All right. So good, little review there. And then this mechanism, especially, you know, the propagations from the first slide here. These ones, you should know them so well that you can just do it in your head. If you have that, then you're good to go with the rest of it. Otherwise, it's really challenging to really draw a good reaction coordinate diagram without having this completely down pat. So just practice it a few times. Okay, now let's look at something I haven't discussed yet. It's radical stability. I have a PowerPoint animation for this. So radical stability, here's the online version. This, I think the online version is good. Oh, and before I do that, actually, let's say this. I want to do a quick review. Remember how I said that different carbons, different hybridization of carbons lead to different electronegativities? And I said, in terms of electro, in terms of electronegativity, I think of sp3 carbons as actually a little bit less electronegative than hydrogen. And then I say the hydrogens are less electronegative than sp2 carbons, which are less electronegative than sp carbons. Oops. Which are much less electronegative than like the nitrogen and the oxygen, you know, and the fluorine. So the key thing though is that I'm saying I like to think of these sp3 carbons as less electronegative than hydrogen. So when they're bonded, they're they're really close, but the hydrogen pulls a little bit of electron density away from it relative. So let's see how that affects radical stability. Go back to this one, radical stability presents. So I've got some radicals here. I have the methyl radical because it's on just a methyl, right? I have a secondary radical because this carbon is secondary. It's got 1, 2 carbons attached. This one, at first, sometimes people think it's tertiary because they focus on the middle one, but this is still a primary radical because it's got the one radical, the carbon that has a radical just has one other carbon attached. And this is obviously a tertiary radical because that carbon is 3. All right, so do carbon radicals have an octet? Do they have, when we do the octet count, is there 8 electrons around there? So no, carbon radicals do not have octets. What's the octet count for a carbon radical? Two, 4, 6, 7. Yeah, this one too. It's got the 2 hydrogens, the primary one. 2, 4, 6, 7. This one 2, 4, 6, 7, and then the methyl, the 3 hydrogens. 2, 4, 6, 7. So yeah, no octet, just 7 electrons. So it wants an octet. It's short. If it's short an octet, is it breaking the octet rule, or is it just higher in energy? So no, it's not breaking the octet. For carbon to break the octet, it has to have over 8. That's breaking. Under is not breaking the octet. It's just high in energy. So can sp3 carbon neighbors help? So if I look at like this tertiary one, it's got an sp3 carbon neighbor right here. sp3 carbon neighbor there, sp3 carbon neighbor there. Do you think they can help out if this radical carbon is short electrons? So remember I said the sp3 carbons are the least electronegative of our, our main organic elements. So if they're less electronegative, the sp3 carbons, that means they might be able to like actually, they don't pull electrons away from you, they can donate electrons into you. So yeah, they can help. We will think of sp3 carbons as electron donating this year, and it'll be used a lot. It'll help us a lot when we talk about carbocations later, when we talk about a lot of reactions, we'll be using this concept. So yes, sp3 carbons, we'll consider them electron donating relative to a hydrogen atom. That's our like standard, because we say they're less electronegative than hydrogen. Okay, so with that in mind, Who is the most stable carbon radical here? Who's the lowest in energy? I think that's what my next click will tell me. Do you think the methyl's lowest in energy, the secondary carbon radical, primary or tertiary? Let's see. Ooh, oh, the tertiary is going to be down here in energy. So the reason why is this is how I want you to think of it. The carbon radical does not have an octet, just has 7. So it's like thinking, oh, I wish I had an octet, but all I have is 7 electrons. Can anyone help me? Any electron density will help. So it's asking its neighbors for help because it's short on electrons. What is this neighbor over here? I'm an sp3 carbon. I'll help because sp3 carbons are electron donating. So they're going to donate some electron density to help out with this carbon neighbor that's short. What about the neighbor over here? I'm an sp3 carbon too. I'll help. And then the last one. Now trending on Twitter, sp3 carbons donate. Oh, there needs to be a space there. So yeah, this tertiary carbon radical has 3 neighbors helping to donate electron density to it to help stabilize it. So that's why I put it the lowest in energy out of all these. What do you think is the next highest in energy after tertiary carbon radicals, the lowest energy? Yeah, the secondary. Because the secondary carbon radical it's short electrons, it only has 7, and it's got an sp3 carbon here. And will it help? Yeah, it'll donate. So I got you, dog, double G. And then this carbon here, it's also an sp3 carbon. And I'm here for you, electron challenge friend. It'll help out, right? But now the hydrogen, I said it's more electronegative than sp2 carbons. So relative to it's more electronegative than sp3 carbons. So relative to those sp3 carbons, it's not donating electrons. So we can think of it as like not donating, not withdrawing. It's the reference. So short on electrons sounds like a personal problem. So the hydrogen is not helping out here. So what do you think is next highest in energy after tertiary is lowest energy, secondary is next, and then the primary, yeah. So the primary radical is short electrons, only 7, wants 8. It's got this sp3 carbon over here that can help out, right? Lean on me when you're short electrons. So yeah, it's gonna donate in, right? But what about the hydrogens here? Will they help? We're busy. No, they're not helping. So it's only got 1 neighbor helping out. That's why it's higher in energy. And then the methyl obviously would be the highest in energy because are the hydrogens helping out? You know, so they're not helping at all. So that's going to be the highest energy radical to form. Okay. With the radical stability. Okay, cool. So now let's look at another animation. I know I'm doing a lot of animations right now. Maybe I shouldn't do it. I've got a lot of animations, but I think it's kind of boring when I just click through animations. Yeah, that's okay. I'll do it. So I have this Hammond postulate animation by one of my former honor students, Nabaha, from 2017, pre-COVID. All right, so let's look at this. So I was trying to come up with a good way to explain the Hammond postulate, like to help you visualize what's going on. And so I outlined this on scratch paper for Nabaha to make this animation. She did a pretty good job on it. So she's got some like definitions of the Hammond postulate, and basically the Hammond postulate's guessing what the transition state looks like, because we're saying it looks more like whatever it's closer to, reactants or products. I can let you read through it a little more. I'm just going to go through this part quickly. So the transition state for an exothermic step, this is exothermic, it's going to look more like the reactants because it's closer in energy to the reactants. Where if you have an endothermic step, the transition state is going to look more like the products. So it seems like pretty reasonable, right? Whatever your transition state's closer to, that's what it looks more like. So example, bromination. So when we have radical halogenation, you can see we weren't so good with curved arrows back then. But so we make our two radicals initially, right? And then propagation step 1 for propane, drawing some hydrogens, emphasizing those 2 electrons there. And we make what kind of radical is this? Is this radical primary, secondary, tertiary? Secondary radical, yeah. So this carbon radical shorts some electrons. It's got 2 neighboring sp3 carbons donating to it to help stabilize it. So it's got some stability to it. What would be more stable? Well, actually, let me keep going on. I'm going to do propagation step 2, bring in the bromine, boom, boom. There we go. And then now let's talk about the reaction coordinate diagram transition states for this. So propagation step 1 is endothermic, the one right here. We're going to focus on propagation step 1. This is the key step that determines what products we're going to get, because whatever radical you get, that's where your bromide ends up. So this is the key step. This step is endothermic, so it's going to look more like the reactants. So let me make sure this makes sense. So it's endothermic, so it looks more like the products. Sorry about that. It looks more like the products. So it's going to have this bond almost fully formed, the HBr, and then the carbon hydrogen almost completely broken. So did you see how we draw that CH bond long? It's almost completely broken, and the HBr short, almost formed. So this transition state, it's going to look, because this carbon hydrogen bond is almost completely broken, it's going to look mainly like a secondary carbon radical. It's going to look right there. And we know secondary carbon radicals are pretty stable. They have 2 sp3 carbons donating to them. So let's break it down and watch as it happens on this Hammond postulate. So when the reaction begins, the bromine is far away from the alkane and it comes on over, and once it gets close enough, it can start to rip off this hydrogen. And as it's ripping off the hydrogen, initially at the beginning, the hydrogen carbon bond's only a little longer than normal. And this HBr bond that's going to form is super long and weak at this point. But as the reaction proceeds, you see how the hydrogen is getting closer to the bromine and further from the carbon. I'll back it up once to see how the hydrogen's right there, close to the carbon. It's getting closer to the bromine. And then it moves up. By the time it gets to the transition state's almost at the final product. So the hydrogen's right up next to the bromine. And then in the final product, you get right before the final product, the hydrogen is like almost to the bromine. It's overlapping a little right there. Yeah, I like that. Annalise is saying, is it on a conveyor belt? You could think of it that way. Yeah, it's on a conveyor belt. It's being transferred over to the bromine. I like that. And then for the final, when you get to the product, you have HBr and the radical, and they can be, infinity apart from each other at this point. They're not associated. Okay, so the key thing here is that because this step is endothermic, the transition state is going to look more like a carbon radical and less like a bromine radical, because we started with a bromine radical and we end with a carbon radical. All right. So here's the kind of the summary of it. I want to remake this with, instead of dashes, I want dots and just a little cleaner. I like, oh, no lone pairs on this bromine, no lone pairs on that bromine, but still it's getting the point across. It's good. So we start off with a bromine radical, end as a carbon radical. Transition state basically looks like a carbon radical because it looks more like the final carbon radical. And it's not just a carbon radical, it looks like a secondary carbon radical. Okay. So if we look at the 2 key steps, what happened here? The 2 key steps of this reaction. The key step is the propagation 1, where the bromine can collide with the primary, one of the primary carbons to give a primary carbon radical, or with the secondary to give a secondary carbon radical, then that's going to determine the final product. So they're both endothermic. I worked it out here, or Nabaha worked it out. So we have the carbon hydrogen bond for a primary carbon hydrogen bond. This carbon hydrogen bond takes 105 to break, where a secondary is a little easier to break, 102. They both release 87 when the HBr forms. And so they're both endothermic, plus 18, plus 14. Okay. So the transition states, they both are endothermic. They both look like products. So we already did this one here. We said in the transition state for secondary, the hydrogen's like right up next to the bromine, almost completely formed. The CH bond's almost completely broken. So this transition state looks mainly like a secondary carbon radical. This transition state for the primary, it's also product-like. It looks mainly like a primary carbon radical. So do you think these two transition states are the same energy? The secondary carbon radical transition state and the primary carbon radical transition state? Now they look different energies, huh? Which one looks lower in energy, having a transition state that basically is mostly secondary carbon radical, or a transition state that's mostly primary carbon radical? Yep. This one's going to be lower in energy. The transition state looks mostly like a secondary carbon radical because it has 2 sp3 carbons helping to donate to stabilize it, whereas the primary only has the 1 sp3 carbon donating to help stabilize it. All right, looks most like primary carbon radicals. Yeah. So when we put these both on a reaction coordinate diagram, this is I'm only showing one step of the whole mechanism, right? Just propagation step 1. You can see we say the secondary is lower in energy because the secondary radical has 2 sp3 carbons donating. The primary only has the 1. So the transition state, which looks like the secondary carbon radical, is going to be lower than the transition state that looks like the primary. Okay. And then I'm going to draw this one out because I feel like I'm just clicking too much for you, but I think you're following along. So if I do this reaction with fluoride instead of bromide, the fluoride is interesting. It's HF bond that forms. It's stronger than the carbon hydrogen bonds that are breaking. And it should make sense to you because remember the HBr bond was only 87, but the HF is 136 kcals per mole to break. So does anybody have a reason why that makes, like, it makes sense to me that HF bonds are harder to break than HBr bonds. Does anybody have a guess at why that is? It's kind of related to electronegativity, but I was thinking more along the lines of what's a stronger acid, hydrobromic acid or hydrofluoric acid? No, no. So HBr's pKa, HBr is below HCl on the periodic table, right? Here, I'll put this. Let me pause this. I'm gonna go back. Good thing I asked. You all got it wrong. Fluorine gets too much credit for things because it's the most electronegative. People make it the highest of everything, but it's not the case. So when we go down the periodic table, when we look at like HF, HCl, these bonds get longer because the atoms get bigger. HBr, who's the stronger acid? What's the trend for acids? So you go down the periodic table. And I'll look at the conjugate bases. Here we go. Minus. So in terms of stability, well, I'll do this. Size, it increases down, right? And then stability. Who's this more stable conjugate base? Stability increases down too. So this is the most stable, weakest base. because it's got a large area to spread out the negative charge. Okay, so bromide's the weak, most stable. It's also, that makes it the weakest base. So what's the strongest acid? Strongest acid. And this is our weakest acid. We've memorized one of these pKa's. What's the pKa of HCl? Minus what? -7, good. Bromide, you might look it up. It's going to be different. It might be, some places will say like -9. And then, did I enable it? Are we getting live transcript? Yes, we are. Good. Who requests the live transcript? I like the live transcript. I just forget to do it. It's, if you're shy about it, you don't have to tell me, but I think it's a good idea. All right, so HBr is -9. It turns out HF is about 2. It's a positive one. It's not even considered a strong acid. If you remember back to General Chem, you learned that, oh, there's strong acids are HCl, HBr, HI, sulfuric acid, perchloric acid, but you didn't memorize HF as a strong acid. Its pKa is positive. It's strong in other ways, but it's not a strong acid. All right, so back to, oh yeah, so let me just say this before I go back. So if this is the weakest acid, do you think its bond is stronger or weaker than the other ones? It's a weak acid, it's going to be hard to break. Stronger bond. And the bond energy for that, the energy it takes to break that bond is not there. Where did I have that? It's like 147 or something. Honestly. $87 for bromine and 136 for fluorine. $136 kcals per mole to break that bond. This one only takes 87 kcals per mole to break it. So it's easier to break the strong acids bond. That's why it's strong acid. It breaks quick and easy. Yep, a lot of general chem in this stuff. Okay, so we got that, and then I'm going to draw this one out for you, but I want to just get this data first. So because the HF that forms is a weak acid, it's got a strong bond, it releases a lot of energy when it's formed. It releases more energy than it took to break the carbon-hydrogen bonds. And so this reaction is not endothermic like the bromine, it's exothermic. And that's going to change things a lot. That means in the transition state, it's going to look more like reactants. So it's going to look more like a fluorine radical for this primary product and more like a fluorine radical for the bromine product. So let me do that on the, I'll do it on the Jamboard. This one's kind of like a long story, but if you work your way through it and understand it, it's nice. It's like, oh, okay, that makes sense. So let me try to do that for you. Let's pick, we'll do the, I'm going to do this mechanism really fast to show you how I want you to be quick about this. All right, we get this and this. So we have initiation. Oops. Boom, boom, making radicals, radical dude. Okay, and then we got a propagation one for the primary, say. There's 2 electrons in this bond. One's coming over, one's going there. Got our primary carbon radical, our hydrofluoric acid. This step is exothermic because we're releasing more energy with that HF bond than it took to break the carbon hydrogen. And then the next one will be, this will run into a fluorine F2. This one's exothermic as well. So meet me halfway. Right on the borderline. For you. Make another fluorine radical. All right, so I can do some terminations, but I won't. I'll just do right now. I'm just going to be doing the propagations because that's what gives us most all of our product, and that's what we're going to put on the reaction coordinate diagram. So here we go. Meet me halfway again. Propagation step 1 for secondary. This is exothermic because this HF bond, weak acid, releases a lot of energy. Got it. And then run into another F2. That came out kind of sloppy. Let's fix that up a little bit. There we go. Oh, oh, oh. Boom. We have 2 electrons in this bond. One's meeting. It's kind of ugly. Let's do a little better. Trying to be fast, but not too sloppy. Meet me halfway. All right, there we go. Done. So let me shrink this down and give me some room to do the reaction coordinate diagram. Is that too small? I think that's okay. All right, here we go. Energy reaction coordinate. There we go. Start off with F2. It's endothermic to make the fluorine radical because you're only breaking bonds. That's got to be endothermic. Takes energy to break bonds. And then the next step is exothermic. And that's where it differs from bromine. So I'm going to draw my carbon radicals. I've got 2 of them. Which one's going to be the lower energy? Is it going to be the secondary carbon radical or the primary carbon radical? Actually, I'll do them in different colors too. Which one's lower in energy? Secondary? Yeah, secondary is lower in energy because it's got 2 neighbors helping to stabilize it. There we go. So we got the primary HF. So this transition state that leads to the primary carbon radical right here, transition state primary, it's going to be pretty much the same as the transition state that leads to the secondary. So the activation energy is going to be almost identical to the activation energy primary. So that means that we're going to make about the same amount of this secondary and the primary radical because their activation energy is the same. They're made just as fast. So let's draw them out. So what is this transition state? Do they look more like the products or the reactants of that step? Products or reactants? Like reactants, huh? Closer. They're closer to the reactants. You can see they're only like, boom, this far away from the reactants. The products are further in energy away, right? Okay, so more reactant light. Let's draw the transition states. So the primary transition state, it's going to look like this. It's got the carbon with the hydrogen just starting to break away. It's early on in the conveyor belt, and the fluorine super far away. I'm going to try to really exaggerate it. Okay. Whereas the secondary transition state looks like this. Hydrogen is just leaving that carbon. Fluorine is really far away. So what does this primary carbon transition state look mostly like? Does this look more like a primary carbon radical or fluorine radical? What do you think? I wouldn't say a primary fluorine radical, Ryan, just say fluorine radical, because there's not really. Yeah. So this one, I'll say it looks approximately, basically it just looks like a fluorine radical. Just looks like a fluorine radical. What about the secondary? Does it look more like a secondary carbon radical or fluorine radical? Like a fluorine radical. So since they both look like fluorine radicals, should they have a big difference in energy? Nope. So should the activation, since the transition states are about the same energy, their activation energies are about the same, their rate of formation is about the same, so we get about an equal amount. We'll get a slightly more amount of the secondary than the primary, but not a big difference like with the brominations. And then if you want, you can try to like finish off this diagram. I'll put this in. Well, I haven't talked about this. So I think this is do on your own. Finish. This is reaction coordinate diagram. So do on your own. So try to finish this off like oh, and then the last step is prop twos are exo and overall reaction is exo. Yeah, it's yeah, sorry, I was drawing it fast. I wasn't necessarily thinking you were copying along exactly with me. But don't feel like you have to like rush through and copy everything I'm doing right now, because these are going to be online afterwards too. All right, so let's look at some relative rate data. You know what? Let's do the bromine one too. By hand. I think it's good to see it by hand. So if I'm looking at the same reaction with bromine, ugh. So it's propane, Br2, and light. Did I switch pages? I did. Secondary bromide, primary bromide, HBr. Oh. All right. So that when I get to that, I'm just going to key in on the step. Actually, I'll start at the beginning. It's easy. Br2, endo, Br radicals, alkane. And now this one, it's endothermic. It's not exothermic like the bromine was. It's endothermic. So what's lower in energy, my primary radical or my secondary radical? Secondary radicals lower in energy, so primary here. And then secondary here. Okay, so my secondary radical is going to go like that, and then my primary is going to go like this. And you see how I just naturally draw them at different energies? It kind of just comes out normally anyways with this. So this is secondary, primary. The activation energy is much different for the primary over the secondary, huh? When you're drawing them, because it's Indo, it just sort of works out. It looks like obvious, but let's explain it. Let's go through it. So let's draw the transition states. So for the primary transition state, what does it look more like? Reactants or products? Is this transition state closer to the products or is it closer to the reactants? Looks more like the products. So that means this hydrogen is going to be almost completely gone. So does this transition state look more like a carbon radical or bromine radical? And it's looking like a primary carbon radical. Transition state secondary, it's going to have that hydrogen almost completely removed. And so it's going to look more like I'm going to say approximately a secondary carbon radical. So this means that that transition state should be lower in energy because we know secondary carbon radical is lower in energy than primary because they're got two sp3 carbon neighbors donating. So I'll say also finish doyo, finish this. So when I do the doyo, I mean like later when you're going over the lecture notes, you can complete the rest of it. All right, so that's kind of cool, huh? See how the Hammond postulate can help us describe how our transition states look, and then use that to explain our data we collect, like why we get more secondary than primary, a lot more secondary bromination than primary, whereas fluorine, we don't get a very big difference in secondary and primary. So let's actually calculate those yields. So let's look at so I showed you last time this relative rate data, and I'll bring it up again. And when I ask you to do questions like this, I'll always give you this data. You might, like me, memorize it after you've used it a few times, but if you haven't memorized it, you don't have to. I'll always give it to you. So here's the relative rate data. So we used primary carbon hydrogens as our reference. So here's a primary. So we say like fluorine reacts with the primary carbon radical, primary carbon to make a radical at a rate of 1, chlorine at 1, bromine at 1. And then we see when we go to a secondary carbon hydrogen bond, when we react to the secondary carbon, the fluorine reacts 1.2 times faster than it does with the primary. Chlorine 4 times faster, but bromine is very selective, 80 times faster. And then tertiary bromine reacts at 1.4 times faster, just a little bit faster. Chlorine 5, not much of a difference. Bromine's big, 1,700 times faster. Okay, so let's use that to predict our product ratios and predicted percent yields. So for the fluorination one, how many hydrogens do we have that can react to make the primary fluoride? There's 2 different carbons, Ryan, but 6 hydrogens total, because this carbon has 3 hydrogens. Think of the fluorine radical. It can run into one of the 3 hydrogens here or one of the 3 hydrogens there. So it's 6. So we've got 6 hydrogens to make this product. Could be ran into. What's the relative rate of the primary? This is, of course, we're talking about primary here. So I come down here, primary, that's the reference, it's 1, yeah. So it's times 1. So this is going to be a value of 6. And now for the secondary products, how many hydrogens are on the secondary carbon that the fluorine radical can maybe halfway like that? How many hydrogens are here? 2 hydrogens. So, and what's the relative rate of secondary? It's a little bit faster. 1.2. So it's 2 times 1.2. So this will be 2.4. That's the relative rate of that one. So what's our major product? What are we making more of, the primary or the secondary? We're actually making more primary for this, but not a lot more. Let's do the percent yield. It's going to be 6 over 6 plus 2.4 times 100, which equals 7.71%. I don't like the way I'm doing this. It's not below it. That's 71% yield is what we're predicting for that one. But the other one, it's 2.4 over 6 plus 2.4 times 100. And that is 29% yield. So yeah, it's our major product. But we still get a lot of that secondary fluoride. Okay, let's do, I want this smaller. I want to fit these both on the same page. Let me make this smaller. I'll make the whole thing smaller, actually. Now let's check brominations. Oops. Okay. So how many hydrogens does can the bromine radical collide with on the reactant? How many hydrogens to make primary? 6 hydrogen. And what's the relative rate for bromine? Just 1, huh? That's our reference. So the bromine is going to make a ratio of 6 of these primary bromides. How many of the secondaries? How many hydrogens for the secondary? 2 hydrogens times a rate of 80, much faster, huh? For the secondary. That's primary, that's secondary. So we're going to multiply by 80. So we're going to get 160. So what's our major product in this case? The secondary bromide is major. We're going to make more of that. It's major. It's the major product. So we can do a percent yield again as well. 6 over 6 plus 160 times 100 versus 160 over 6 plus 6, 160 times 100. So what do I wind up with this math? 3.6% of the primary, not much. And 90, what do I got there? 96.4%. So that's definitely major, huh? Bromine's real selective. When I say major, sometimes I think of, I saw like an interview or something with, who's the famous Spice Girl? Not Sporty Spice, Posh Spice. Was it Posh Spice? She was saying major a lot. Oh, that's major. I thought it was funny. I think it's interesting when certain words become popular and used a lot. I feel like, what's the word that was used so much? Vibe. I was listening to some like YouTube video and this guy said vibe like every other word. He said vibe like 20 times in a paragraph. Like, yeah, I'm just vibing, you know, just gotta have the good vibes. And you're vibing, vibe. I have a lot of words I repeat too. I say a lot of things. Okay, so anyways, back to this guy. So yeah, and we can explain this with the Hammond postulate. So we can say the difference in activation energy to make the secondary radical versus the primary for bromine is big because the secondary, it looks like more like a secondary carbon radical than a primary carbon radical. So that means it's faster to form the secondary carbon radical, which leads to this product. It's 80 times faster. Whereas with the fluorine, the activation energy to make the primary and secondary radicals about the same because it's an exothermic, it's exothermic reaction. Transition states look like a fluorine radical, look like a fluorine radical. So it's only 1.2 times faster. Okay, we are killing it. I have another slideshow to show you. This is a good one. I'm going to do it kind of fast. I already did, so don't try to write this down. I mean, it's an animation that you can click through. And I went ahead and put these animations in the homework. So I'll show you real quick. So these animations we've been going through, you're going to go back through them when you do homework C. So it's good to look over your notes, but if you want, you can just start on the homework and you'll see that it's kind of forcing you to go through your notes. So you do the brobromination. I guess this one you're doing on your own, but here you're going to look at radical stability we did today, Hammond postulate, Nabha we looked at today. And then this one. This one I made up, I like kind of hand drew it on the Jamboard, which I don't like as much as when I use Marvin Sketch, but then I don't know, maybe I should just do them all this way. I don't know. I slow myself down on how I can make these kind of animations because I want them to look really crisp and clean. But I feel like the rest of the world is doing this kind of drawing, hand drawing on YouTube videos like the Khan Academy and stuff, and they can generate content so much faster. But whatever. Here's my Hammond postulate. Radical halogenation of alkanes, Hammond postulate considerations. Sorry. I don't think this is COVID. I was eating these addictive nut clusters from Costco, and if I eat those and I don't drink enough water right away and I start talking, I start coughing. I think I'm okay. Mark saying, don't write this down. I like that, Ryan. All right, so here we go. So I have a cycloalkane here. This is methyl cyclopropane. We're actually, after I do this example, we're going to start on the chapter of cycloalkanes. So what kind of products can we get? What you can do to help you determine what products you're going to get is think of it in terms of like carbon NMR and circle your groups of carbons. So this methyl is unique, that tertiary carbon's unique, and these two secondary, they're the same, right? So I could see 3 different regions the molecule will react, or what we say is we can get 3 different regio products. So I'm going to draw up the alkane again, just exactly as it started, and then add on the bromines. So that's the primary, tertiary, secondary. Nice, right? So what do you think is the major product out of these three? What's your first guess without doing any calculations? Stop top of your head. What do you think we're gonna get the most of? Yeah, the tertiary. Let's check it though. So for the primary, there's 3 hydrogens and reactivity of 1. So that's a 3 ratio. Tertiary, there's only 1 hydrogen to react at the tertiary position, but it reacts 1700 times faster than primary. Secondary, there's the most hydrogens, 4, but they just react 80 times faster than primary. So the ratio is going to be mostly tertiary, then a lot of secondary and very little primary. Okay, major, most minor. All right, so, oh, and I did work out the percent yield of the major, 84%. So yeah, and I bet it's like 1% less. That's less than 1% most minor. This is going to probably be like what, like almost 16%. You can work it out. Okay, and then let's look at the mechanism. We have the initiation first, and I'm drawing the bond in red. I use colors on this one, so you can see I got a red radical there. No radicals, 2 radicals. And now I'm going to work on the primary mechanism. So I'm using a red radical on the bromine from before, and I made the bromine blue. Maybe I should have had this blue, but I think I used black here, but then I used for prop 1 and 2. I was trying to be good with the colors, but there's only so many colors. But so I got a green there. And then boom, I got my red matching, running into my green going there. So I got a green radical, a green red bond. So I don't know what remnant means. Ask me later about that sentence. All right, so now, am I repeating it? Oh yeah, I was just kind of labeling the colors there. Okay, and now propagation step 2 for the primary. I'm doing the same thing. 1 red electron goes to that bromine, 1 meets up. Meet me halfway. There they are, right? Looking good. Okay, now for the secondary propagations. So for these ones, the bromine is not going to collide with that methyl up top. It's going to collide with the one of the 4 secondary carbons. And there we go. We got like a red and a blue electron meeting up there. Blue radical on the carbon. And then this carbon radical is going to react with the bromine with 2 red electrons. So we get that red, blue. All right. And now tertiary. We go with went with yellow on this one and blue bond. So the red and the blue are matching up. And then the blue with the red. There we go. Bam, bam, bam. We got them all, right? Hopefully these mechanisms are starting to really get stuck in your head. Okay, so lots of terminations are possible, but I'll let you draw them because we're just going to focus on these for now for our reaction coordinate diagram. So this is going to be a big one. This reaction coordinate diagram, I'm going to show the initiation, all the propagations, and no terminations though. So here we go. So we start off with bromine becoming a bromine radical. Why is that one endothermic? Can anyone tell me why that would be endothermic? We're only breaking bonds. That's right, James. It takes energy to break bonds. No bonds are formed, so you know it's endothermic. Next up, I'm drawing I'm drawing the alkane 3 times in 3 different colors, because remember before my mechanism was in 3 different colors. And then, so the blue one was the primary radical. Does it make sense that I've drawn this primary radical kind of high in energy? Yeah. And it looks like so Annalise is saying it looks like oh, this one looks like an Erlenmeyer flask. It does. And now it looks kind of like a coat hanger almost. I don't know. Yeah, primaries are high in energy. Secondaries lower in energy because the secondary carbon radical has 2 sp3 carbons attached that can donate electron density to help stabilize it. And the tertiary will be lowest in energy because it's got 1, 2, 3 sp3 carbons electron donating to help out. So we've got our 3 carbon radicals. All of our transition states are closer in energy to products. So this tertiary carbon radical, this tertiary transition state looks like mostly like a tertiary carbon radical. Secondary transition state looks like a secondary carbon radical mostly. Primary transition state looks mostly like a primary carbon radical. So there's differences in energy there. Then we add in our next reagent. These are the products of prop 1. Now we need to add another reactant for prop 2 because that's what the carbon radicals react with. So these ones, the transition states we don't need to focus on them that much. They're about the same because I don't really need to worry about the difference in energy for these, because once I have the radical, the carbon radical, my fate as to what product I get is determined. So the initiation at this point, I don't know what kind of product I'm going to get after this step. Oh, I know I'm going to get a tertiary bromide or secondary or primary. And then this last step is just, finishing it. Okay, so we got our 3 products there. And this is the initiation, propagation 1s, propagation 2s, right? Okay, so now no terminations included. It's just too much and they don't make much product. All right. And then initiation product like bromine bond is almost completely broken. So this transition state here, the first initiation is looking like the product. So I'll draw it. I'm reminding you of the mechanism and I'm showing you it's super long, right? The transition state between the reactant and product. It's long like the products. All right, and then these ones are the key ones here, huh? Prop 1 primary, product like, it looks mostly like the product. Hydrogen HBr bond is almost completely formed and the carbon hydrogen bond is almost completely broken. So can you meet me halfway? So this bond is short, it's almost fully formed. That's almost totally broken long. And so this looks mostly like a carbon radical, a primary carbon radical. And then for the secondary, same thing. It's closer in energy to the products. It looks almost totally like a secondary carbon radical, the transition state, long, short. And the tertiary, again, the same. It's looking mostly like a tertiary carbon radical, long, short. I'll meet you halfway. All right, so prop 2s. They look like, oh, you guys tell me, what does the blue primary, secondary, primary prop 2's transition state look more like? Does it look more like the reactant carbon radical or more like the product bromine radical? More like the reactants. Good. Let's do it. So I draw them all up. So they look more like the reactants. So this carbon to bromine bond's really long, and this one's short. Really long, shorter, really long, short. And don't forget you have 3 lone pairs on this middle bromine. It's easy to leave those off. Just tell me where you want to go. Just tell me where you want to be, want to meet. All right, and that it? That's it on this one. I thought I would have done more about more radical like, more carbon like. That's all right though. Okay. Ooh, yeah, this is a good lecture today. I hope you felt like I not only learned some stuff, but I didn't just like learn what I need to go learn later. I'm hoping it's starting to stick in right now. Good. Should I do a couple of minutes on chapter 4? We're done with chapter 3 now. Or should we pause there? We'll pause there. So we'll start up with chapter 4 on Monday. START. 10/2021.
Dr. Spencer,
Yeah.
on the hydrogen bromide, so that's in the initiation, or actually propagation step 1, is that an actual product that we draw out on the final products?
Like-
Hydrogen bromide. In other words, should we draw it on the coordinate diagram?
Yeah, I got it like right here, right? See all these HBRs, is that what you mean?
Right, and the final.
In the final step of the diagram?
Uh-huh.
Like right here, do I redraw HBR, do you mean?
Right, yes, sir.
No, don't do that. You're just showing, this isn't like you're showing how things, when they form, that's when you draw them. Like you draw the bromine radical when it forms here.
Uh-huh.
HBR is made here. You don't draw it again.
Thank you, sir.
Welcome.